Okay, good evening, everyone. I welcome you all to the crash course of eCal Academy. So, I hope everyone is all right. Okay, so yesterday we discussed about the chemical properties of metals and non-metals. Today we are going to continue few more chemical properties. Let me share the screen. Okay, so I hope the screen is visible to all of you. So we were discussing about aqua regia yesterday. We left on this slide. Aqua regia is a mixture of two acids, nitric acid having the formula HNO3 and hydrochloric acid having the formula HCl. One part is nitric acid and three parts are hydrochloric acid. Now both of them are strong acids. Both are very strong acids. Now when we mix these two strong acids, the mixture that we get aqua regia is really very corrosive. It is very corrosive. It is such corrosive that it can dissolve gold, even platinum. It can dissolve both gold and platinum. So it is this corrosive in nature. Otherwise, gold and platinum are the noble metals which will not react with the acid. So here you can have 1 mark question asking you the definition of aqua regia, or you can have MCQ where they can ask you the ratio of the two acids, or you can have a MCQ asking which acids are mixed. So this way you can be given the question based on this information. Now you can see a lengthy question in front of you. A man went door to door posing as a goldsmith. He promised to bring back the glitter of old and dull gold ornaments. An unsuspecting lady gave a set of gold bangles to him, which he dipped in a particular solution. The bangles sparkled like new, but their weight was reduced drastically. The lady was upset, but after a futile argument, the man beat a hasty retreat. Can you play the detective to find out the nature of the solution he had used? So I'm sure you must have got the answer. The solution he used was aqua regia. Now, as we discussed in the previous slide, that it is very corrosive in nature. So what happens to the old and dull ornaments, golden ornaments, when you put them in aqua regia? The uppermost layer gets dissolved. The uppermost layer gets dissolved. Now, when this layer gets dissolved in aqua regia, the new surface gets exposed is very shining. The surface is very shining. So it seems as if the gold ornament got cleaned, but actually the upper layer got dissolved into it. So when imagine now if in a same beaker having aqua regia, one by one you go on putting gold ornaments, the gold keeps on dissolving into it, which can be recovered later by making it evaporate. You can make aqua regia evaporate, you will get back the gold. So this was used for this kind of cheating by some people a few years back when people were not aware about this aqua regia. So you can see the answer over here. Now, the next property is the reaction between non-metals and acids. As we discussed yesterday, that non-metals do not react with water, they do not react with acid also. They do not react with acid also, because the reason is very simple: they cannot give electrons, they can't give away electrons, right? So these were the few chemical properties of acids and bases. We will be continuing with few more. Let me share that screen with you. All right. So the next part of the properties of metals and non-metals we are discussing now. Okay. So you can see the screen over here. Just a second, I'm just sharing it. Okay. So you can see the reactivity series in front of you. Now here, one reaction is shown. Iron is reacting with copper sulfate. This is iron reacting with copper sulfate solution. So we can see the position of both the metals over here. The position of copper is here and iron is here. So as we know that the metals which are towards the top of the reactivity series are more reactive, and when we go down the reactivity decreases. So it is quite clear that iron is more reactive than copper. This is less reactive. So in this equation, iron is more reactive, and moreover it is free. It is not in a combined state. So it will displace copper from its position, and we will get ferrous sulfate and copper. You can see it is ferrous sulfate and copper, right? So this happened because iron is more reactive. If it was the other way around, suppose you get copper which is reacting with FeSO4. So we know that copper is less reactive. This copper is less reactive. It cannot displace iron. This cannot take place. It cannot displace iron because copper is less reactive. So nothing happens. It simply lies. It simply lies in the ferrous sulfate solution, right? So before we can predict the reactions over here, we should know which one is more reactive. We will see one more example. Here you can see magnesium is reacting with copper sulfate again here. So magnesium is more reactive. This one is more reactive. So it is capable of displacing copper. So we'll get magnesium sulfate and copper, right? So you need to memorize the reactivity series if you want to answer these kind of questions. Now we have zinc and copper sulfate. This is zinc, this is copper sulfate. Again, zinc is more reactive than copper, so displacement will take place. Then we have copper and silver nitrate. This is copper and this is silver. So here copper is more reactive than silver, so it will displace silver. So we get copper sulfate and silver is free now. So in this concept, you can be given the half equation and you are supposed to predict what is produced. So you can predict only if you know the reactivity series, right? So displacement reaction is the one where a less reactive metal gets displaced by a more reactive metal. And a very common example in this case is displacement of copper by iron nail. The color of iron nail is gray over here. And this solution is blue copper sulfate solution. But after the reaction takes place, you can see this light green. This is light green copper sulfate. And the iron gets a coating of brown, reddish brown. reddish brown copper metal gets deposited on the iron. So it makes clear that the reaction has taken place. You can see this. The iron nail got a coating of reddish brown copper, right? Now this was just the picture, but this is the photograph, real photograph of this. You can see this part of the iron nail got copper deposit. This part, right? And these pieces that you see are the pieces of copper that have got displaced. Okay. So this is another reaction, another example, magnesium put in copper sulfate solution. After some time, it becomes magnesium sulfate, which is colorless. This is colorless. And magnesium, which is silvery white in color. This is silvery white in color. It got a deposit of reddish brown copper. The same thing happened over here. The displacement took place. Right? Now, we have another reaction here. You can see in this reaction, the metals are reacting with salt solution. Two examples we have seen with the diagram. Here we can see few more examples. Right? So you can see this everywhere the displacement took place. Now the reaction of non-metals with salt solution. You can see here chlorine is a non-metal and it is made to react with aqueous solution of potassium iodide. Now iodine got displaced by chlorine. So chlorine is more reactive. Chlorine is more reactive because it was able to displace iodine. The next example shows that chlorine is able to displace bromium. This chlorine is able to displace bromium. So chlorine is reactive then bromine also. Chlorine is reactive then bromine also. Right? So the displacement can take place in non-metal also. A more reactive non-metal can displace a less reactive non-metal. These two examples you have to remember for non-metals. A question based on this concept. Samples of four metals A, B, C, D. You can see these are the metals A, B, C, D are added to these solutions: iron sulfate, copper sulfate, zinc sulfate, silver nitrate. And the result is given over here. Like for example, when A is mixed with iron sulfate, no reaction takes place. When A is mixed with copper sulfate, displacement takes place. So read the data nicely, because based on this data, you will be getting some questions. Let us see what the questions are. So the data is this, and this is the question: which is the most reactive metal? So if you remember, I told you few minutes back that to answer these kind of questions, we need the reactivity series. This is the reactivity series, right? So let us see. See, the names of the metals we don't know, but we know which metal salt solutions are given. First one is iron sulfate. So the position of iron is this. Second is copper sulfate. We can see the position of copper here. The third given here, it is zinc sulfate. The position is zinc. And the fourth salt solution is silver nitrate. So the position of all four metals which are given in solution form are here. Out of all the four, zinc is most reactive because it is on the top. Now, whichever metal out of A, B, C, or D can displace zinc is most reactive, right? Is most reactive. So let us see who is displacing zinc. We can see no metal is able to displace zinc. So we will see the next most reactive after zinc is this iron, right? Whichever metal is able to displace iron. Let us see. See, A is not able to displace, B displaced this, C no reaction, D no reaction. So based on this, B is most reactive metal because it was able to displace iron, right? So first one is B over here. Then the next most is copper. A is able to displace copper, so it is A. And C is able to displace silver, so C is the next reactive metal. So the answer to the question, which is most reactive, is B. See, this is what I have explained is there on screen. Most reactive metal is zinc. B. The next question based on the same concept is what would you observe if B is added to a solution of copper sulfate? So let us see. B is added to copper sulfate. We know B was able to displace iron, so it will be able to displace copper also. So the reaction is BSO4 plus copper. This is the reaction, right? And the third question is arrange the metals A, B, C, D in the order of decreasing reactivities. Just now we have seen B, A, C, and finally D because D is not able to displace any of the metal. So this is how we get the answer, right? Now, the next question is what would you observe when zinc is added to a solution of iron sulfate? So this is zinc over here. We have FeSO4 over here. And the color of ferrous sulfate is light green. And zinc is a silvery white metal. Now, as per the reactivity series, we know which one is more reactive. Take a pause and try to figure it out. Zinc is more reactive than iron. So it will displace and we'll get ZnSO4 and iron is free. The color of zinc sulfate, actually it is colorless. So the moment we see the color changing from light green to colorless, we understand that the reaction has taken place. And the deposit of iron will be seen on zinc. Iron will get deposited on zinc. So this shows that zinc is more reactive than iron. Okay. Now we have one more question. Which of the following pairs will give displacement reaction? Four equations are there, given there in front of you. To find out if the displacement will take place or not, again we need reactivity series. Sodium chloride and copper metal is given. Sodium is most reactive, but it is already in combined form, so it will not displace. Magnesium is more reactive than aluminium, but it is already in combined form. This will not take place. Iron is more reactive than silver, but again, it is in combined form, so the reaction will not take place. Copper is more reactive than silver, but it is in free form, so the reaction will take place. So the answer here is D. The next question, food cans are coated with tin and not zinc because of which reason? Zinc is costlier, it has higher melting point. Is more reactive or less reactive? So the answer is here C. Zinc is more reactive than tin. So these were some questions based on the few more chemical properties, in fact, the displacement reactions. Now we are going to see a new set of chemical properties. Let me share that screen also with you. Okay. So we have here the reaction of metals with hydrogen. Let us see what happens when metals react with hydrogen. Children, normally these all metals do not react with hydrogen, but the ones which are very reactive, like you can see here, sodium, let me highlight it. Sodium, potassium, calcium, magnesium, they combine with hydrogen because they are very reactive. And they produce metal hydrides. Metal hydrides are ionic compounds. And we already know that ionic compounds are the ones which are formed by transfer of electrons. These are formed by transfer of electrons. So metals have a tendency to donate electrons and hydrogen takes it. So the first one is sodium reacting with hydrogen to produce sodium hydride. You need to heat the contents over here if you want to make them react. Same is with calcium and hydrogen. We get calcium hydride. This is also upon heating. So as I told you, these are ionic compounds. Then few more examples are given here. Now we see the reaction of non-metals and hydrogen. Non-metals and hydrogen make covalent hydrides. Covalent hydrides means the ones which are formed by sharing of electrons. These are formed by sharing of electrons. So you can see the example of hydrogen reacting with sulfur to give hydrogen sulfide. You can see the temperature is quite high here. It needs 440 degrees Celsius for the reaction to take place. The next reaction is between nitrogen and hydrogen to produce ammonia. It needs the presence of iron as the catalyst and really a high temperature over here. This is called Haber's process. Haber's process of producing ammonia. So now we reach the last chemical property, the reaction of metals and chlorine. The reaction between metal and chlorine. So you can see here, the first reaction is between sodium and chlorine. You very well know these reaction. Sodium reacts with chlorine to give sodium chloride, which is the common salt. The common salt that we eat is produced because of the reaction between sodium and chlorine. And these are also ionic chlorides. All of them are ionic chlorides. You can see one by one: calcium chloride, magnesium chloride, zinc chloride, iron chloride, aluminium chloride, copper chloride. All are ionic chloride, means metals donate electrons to non-metals. Metals lose electrons and non-metal, the chlorine gains electron. So these are all ionic chlorides. Now you can see the diagram here. This is the diagram showing you the transfer of electrons. We know sodium has atomic number 11. So the configuration is 2 8 1. So it needs to lose one electron so that it is happy with 8 electrons in the outermost shell. So this electron is lost to chlorine, which has total 17 electrons. The configuration is 2 8 7. So if it gains this one electron, it becomes 2, 8, 8. So 18 electrons. So it will develop minus charge, and sodium loses electron to develop positive charge. So you can see here Na plus and Cl minus. So they develop a force of attraction between them. So they are also called electrovalent compounds or ionic compounds. So this should be very clear with everyone that the charges develop because of loss and gain of electrons. So as I told you, these are ionic compounds or electrovalent compounds. A very strong force of attraction is there. Strong electrostatic force of attraction is there, which keeps them bind together. And this is the reason that they have very high melting and boiling point. Non-metals react with chlorine and give non-metallic chlorides, which are covalent in nature. They are formed by sharing of electrons. So they are formed by sharing of electrons. So like as I told you, here hydrogen is a non-metal, chlorine is another non-metal. So the electrons will be shared between them. So there won't be any positive or negative charge. You will not see such thing. So that's why they are not ionic, they are covalent. So these were the 6 properties, chemical properties. Here we see one example, formation of hydrogen chloride. Hydrogen has 1 valence electron, chlorine has 7, 1, 2, 3, 4, 5, 6, and 7th one. Hydrogen shares this electron with chlorine. Here you can see this is the electron shared between them, a shared pair of electron between them. So this creates a bond. This is the covalent bond between hydrogen and chlorine. So this is how the covalent bond formation takes place between hydrogen and chlorine. So we have 2 types of compounds, ionic and covalent, depending on the way they are formed. If they are formed by transfer of electrons, it is ionic compound. If it is formed by sharing of electron, it is covalent compound. Now let us see why covalent chloride is formed. As I already told you, non-metals cannot give electrons. Chlorine is another non-metal which cannot donate electron. So the only way is they share electron. And because they share electron, they form covalent compounds. We already know that metals have a tendency to donate electrons, but it is not that easy. It is not easy. I mean, they will not readily give away electrons. It needs energy to make them lose electrons. This energy is called ionization energy. This energy is called ionization energy. So the ionization energy for metals is not very high, it is low. Ionization energy is less for metals. But for non-metals, the ionization energy is high. So this is one more difference between the two. Metals have low ionization energy. Non-metals have large ionization energy. It needs a very high temperature for non-metals to get ionized. Because metals lose electrons, they are electropositive in nature, and non-metals gain electron, they are electronegative in nature. So when they ask you to differentiate between metals and non-metals, you have a whole lot of difference between them. We have discussed 8 so far. So now we will see the difference between ionic compounds and covalent compounds. The as we know, the ones which are formed by transfer are called ionic compound, the others are called covalent compounds. So one by one, let us see the difference. The first difference is on the basis of the physical nature. Ionic compounds are mostly solid and they are very hard because they have strong force of attraction between them. Covalent compounds are mostly liquids or gases at room temperature. A few are in solid state like urea and sugar. The second difference is in melting and boiling point. The melting and boiling point for ionic compounds is really very high because we already discussed in one of the slide that they have strong force of attraction. This strong force of attraction needs high energy to be broken. So they have high melting and boiling point, but for covalent compound, the melting and boiling point is low because of weak intermolecular forces. It is easy to break away these forces. So melting and boiling point are really high. The third point is about solubility. Ionic compounds are soluble in water, but they do not dissolve in other solvents like kerosene, petrol, or some other organic solvent. Whereas covalent compounds are insoluble in water. They do not dissolve in water, but they are soluble in non-polar solvents, benzene, carbon tetrachloride. They will dissolve in them. So this is the major difference. The fourth and the last difference is in conduction of electricity. Ionic compounds conduct electricity in molten or aqueous form. Molten or aqueous form. Molten means the liquid form of a substance, and aqueous form means dissolved form. It is the dissolved form. So they conduct electricity either in molten or aqueous form, but covalent compounds do not conduct electricity. They do not conduct electricity. So these are the four differences between ionic and covalent compounds based on few criteria. The dot and the cross over here represent the electrons. So in exam, you can have a question to show the formation of sodium chloride with the help of electrons. Show the formation of sodium chloride with the help of electrons. So how we need to show that we will see now. So this is electron dot structure. And how to draw it, you need to know the atomic number for the compound, for the element. Once you know the atomic number, you can figure out the electronic configuration. So electron configuration of the element will be known once you know. Say, for example, here sodium is taken. So we know the sodium atomic number of sodium is 11. So configuration is 2, 8, 1. So it is this shown here. And for chlorine, the atomic number is 17. So 287 is the electron configuration for chlorine. So here you can see the electron configuration with the diagrams for both of them are given. So they will be losing electron, sodium will be losing electron. Now, you can be asked a question here to draw the electron configuration of certain elements or compounds. In this question, you can see they are asking you for sodium. So as I told you, you need to know the atomic number. Atomic number for sodium is 11. Electron configuration is 287. So you know you need to make 3 shells. So you make a nucleus, the first shell around the nucleus, the second shell around the nucleus, and the third shell around the nucleus. You show two electrons within the first shell. You can use either the dot or the cross. And in the second one, you have to show 8 electrons. So 1, 2, 3, 4, 5, 6, 7, 8. And finally, you need to show 7. Sorry, it is 11. So this is 2, 8, 1. So you will be simply uh, making 1 electron here, right? This one. On the outermost shell, you will simply show 1 electron, this one. So this is for sodium. Sodium. Similarly, for oxygen, the atomic number you must be knowing. It is, let me erase the contents. For oxygen, it is 8. Atomic number is 8. So the configuration is 2, 6. So you need two shells. You need two shells over here. In the first shell, 2 electrons and 6 in the next shell. And for magnesium, it is side. So for compound, you will have to show like sodium is 11. So this is 281. It will become stable when it loses 1 electron. Because it loses 1 electron, it becomes positive 2 and 8. So sodium is stable. Now you need to show for oxygen. It is 8 to 2 and 6. It will become stable if it gains 2 electrons, and it will become 2 oxygen minus 2 because it has gained 2 electrons. So the first thing you show here is this. Then you need to simply show the valence electron. This is the valence electron of sodium. And these are the valence electrons for oxygen. 1, 2, 3, 4, 5, and 6. So 1 electron will be donated by sodium to oxygen, but still oxygen is not happy. It needs one more. So in this case, we need one more sodium to donate its electron. So now oxygen is happy. Sodium is plus, but we have two such sodium atoms, and oxygen is minus 2. So the formula for sodium becomes Na2O. This is how you show the formation of the compound sodium oxide, right? Now, similarly, you need to show for magnesium oxide, this one, magnesium oxide. So magnesium is atomic number 12, 282. It will become stable once it loses 2 electrons. So it develops for plus 2 charge, and it will have 2 and 8, right? And oxygen, we already know it is 6, sorry, it is 8. So 2 and 6 will gain 2 electrons and becomes O minus 2, 2 comma 8. So now we have magnesium having 2 valence electrons and oxygen having 6 valence electrons, 4, 5, and 6. It will be donated like this. So it becomes Mg plus 2, O minus 2. Overall, MgO is the compound. Right? So one such question will definitely come in exam. So you need to prepare them. All right. In this way, I give you the homework for calcium chloride, magnesium chloride, and aluminium oxide. You need to do it on your own. And in the next class, we'll see if you are able to draw it correctly or not. I'm repeating: calcium chloride, magnesium chloride, and aluminium oxide. Now, the next question is, what are the ions present in these compounds? So, the ions are magnesium ions and oxide ions, sodium ions, and again oxide ions. These are the ions present, right? Then we have, why do ionic compounds have high melting and boiling point? We've already discussed when we were discussing the difference between ionic and covalent compounds. Ionic compounds have strong electrostatic force of attraction between the ions. So it needs a lot of heat energy to break them apart. So that's why the melting and boiling point are quite high for ionic compounds. Right? So this is the end of